Hi there, welcome to a lesson on homogeneous functions. This video is just kind of an introduction into homogeneous functions, what they are and how we can tell if a function is in fact homogeneous. I'm not going to get into its applications into differential equations and substitution and all that good stuff. I'll get involved in that in my future videos, but for right now, let's just kind of look at the definition I found on Wikipedia here. It's not my favorite just because of how it's laid out, but I'll try to explain it using their notation. So imagine we have a function f of xy, and they used x1 and xn, which I don't love. But all they're saying is, let's say we multiplied each component of the function by some scalar s, right? It's not a vector, it's a scalar. We're multiplying each component, x and y, by some scalar. So the function is now f of sx and sy. Okay, a function is considered to be homogeneous if it can be rewritten as s to the power alpha, or in this case they used k, times the original function f of xy. Okay, so it's important to note that this exponent here, this alpha, or they used k, that's called they wrote it up here, the degree of homogeneity. Okay, so if we can factor out an s squared, right, the scalar squared, that means that we have a homogeneous function of degree 2. So it has a degree of homogeneity of 2. Okay, so let's just kind of come up with some examples here. So let's say our function f of xy was x squared plus y squared. So let's say f of xy equals x squared plus y squared, okay? So we multiply it by a scale factor of s, each component, so f of sx, xy, what's that going to be? Well, if we replace the x we had up here, right, with sx, right, and then the same thing with sy for y, okay, we can kind of replace what we have. This is going to be s squared, x squared, plus s squared, y squared. Now you see how both terms have an s squared in them? That means that we can factor out an s squared and multiply it by x squared plus y squared. So you'll notice that the original function is still kind of embedded within here, x squared plus y squared. We just factored out this s squared, right? And that kind of goes along with the definition they gave up here. That is this part right here. This k in our case is 2 because we factored out an s squared. The degree of homogeneity of this function would be 2 because we can factor out an s squared. That's the degree on the scalar we factored out there. So this function is in fact homogeneous. Let's think of one that might not be homogeneous. Okay, what kind of function would not be homogeneous? So let's say f of x, y. And you might kind of have some intuition. You might say, well, if we have a constant up here, like if this was x squared plus y squared plus 3, well, this kind of throws a wrench into things because we can't factor out an s squared from 3, right? Because no matter what we multiply our components x and y by, this 3 is unaffected, like nothing's going to happen to it. So constants are kind of the enemy of homogeneity, so just keep that in mind. So let's say we have a function, I don't know, x to the third plus y to the third plus 2. Okay, well, if we multiply the components by some scalar x, right, it's going to be sy. We just replace x with sx. It's kind of the same deal. Sy, right? See how this 2 up here, it's not a variable, right? It's a constant. So no matter what we multiply the components x and y by, it's going to remain unaffected. So this is just going to be 2. So this is s cubed x cubed plus s cubed y cubed. So we can factor out an s cubed for the first two, except we got this plus 2 hanging on here, and we're not going to be able to factor it out. The most we can do is we can say it's s cubed x cubed plus y cubed plus 2, but like this plus 2 is kind of on its own, right? So this function is not homogeneous because even though you can factor out um, a third degree or s to the third degree from the first two terms, it has to be factored out of all the terms and it's not for 2, right? Kind of going back to our definition up top. See how there's no constants at the end? This s to the k, in this case for this last one, it would be 3. It has to apply to all the numbers, so this would not be a homogeneous function. All right, so there's just kind of some intuition into what homogeneous functions are. They're helpful when we're solving differential equations because if we can show a differential equation is homogeneous, then we can perform a substitution and a separation of variables, and it'll ultimately make our lives a lot easier. I'll explain this in future videos, like I said, but hopefully this video just gave you some intuition into what homogeneous functions are and how we can kind of solve if they're homogeneous. So I'll see you in the next video.